Hi, I'm Jeff Chow. I'm an engineer at Heroku working on the data team. And specifically, I work on the team that provides Apache Kafka as a service. In today's talk, we'll go over some of the details regarding the challenges we've encountered and had to solve along the way. But specifically, let's first cover some of the core concepts and fundamentals of Kafka. So Kafka is essentially a distributed messaging system, and it consists of 5 fundamental components. They are brokers, topics and partitions, and producers and consumers. Now, brokers are just individual instances or processes of Kafka that manage streams of messages, and these messages are categorized into topics. These topics may have one or more partitions, in which a partition is just a write-ahead log that writes messages in the order that they are received and stores them directly on disk. Now, I would like to point out that Kafka thinks in terms of partitions, where essentially topics are just an abstraction for groupings of partitions. Now, with that said, partitions are Kafka's fundamental building blocks for parallelism and message ordering. And lastly, topics, but specifically their partitions, are replicated across brokers. So that's for the server side. Now, on the client side, we have producers and consumers, and these guys simply just write to or read from a topic, where a producer, although it writes to a topic, more specifically, it writes to specific partitions determined by some key. And otherwise, we have consumers, which simply just read from their assigned partitions. So pretty straightforward so far, but the interesting thing about consumers is that they maintain their own offsets or progress of where they read up to for each partition. Now, why is this useful? Because this means that consumers can process at their own speeds, be it fast or slow, but in addition to that, consumers can individually recover their progress on a failure. Now, this is all great conceptually, but when it comes to operating Kafka, there are many things to consider when dealing with it at scale. It might not be as easy as you think. For instance, how do you deal with replication? Or how does Kafka achieve HA? Then there's quota management and security, as in how do we prevent abuse from misbehaving users? And then there's OS, JVM, and Kafka tuning, and also even managing Zookeeper, which is a talk in and of itself. Now, if we go down the stack and think about the underlying physical or virtual infrastructure, we have other details to consider. Details like networking, growing disk volumes, monitoring metrics, and even a sensible logging solution. So more on the operational side, there are version upgrades, as in even just for Kafka. Forget about everything else. How do you upgrade to a new version of Kafka? And more specifically, what do you do when faced with breaking changes? And lastly, how do you detect when the underlying servers or disk have been corrupted, and then proceed to automate some sensible replacement strategy? So the good thing is that at Heroku, we offer Apache Kafka as a fully managed service with the goal of taking care of a lot of these operational burdens for you so that you can focus on writing data-intensive applications and moving on. And speaking of production, we currently run hundreds of clusters in production, and some of these clusters run thousands of partitions per broker. And we've observed that individual clusters have been processing up to about 150 megabytes per second sustained, so about 13 terabytes a day. And this is for produce and consume traffic with about 5 milliseconds or under 5 milliseconds of latency on a message. We also operate in data centers around the world where all of our brokers and Zookeeper nodes are striped across availability zones for better fault tolerance. And we also have our partitions placed in a rack-aware manner for the same reasons. So this is great, but it took a lot of work to get here. And we were specifically interested in pushing the limits of Kafka at scale so that we could get ahead of any potential challenges that might come up so that our users wouldn't have to face them in production. So what did we do? We went out and built tons of internal tooling and infrastructure around these cases that eventually surfaced a variety of challenges for operating Kafka at scale. In today's talk, we're going to cover 3 of them. So our earliest challenge that we had to overcome had the following observed behaviors. So first, we were seeing that users were exceeding their produce quotas for long periods of time, and this was for many users. Secondly, brokers were crashing and being restarted on some regular basis. And to add to that, we were seeing various network threads on the brokers getting null pointer exceptions. The major insight here was with quotas. Though, for context, at Heroku, we leveraged Kafka's quota implementation, although quotas in Kafka might not be implemented in the way you think. You see, Kafka favors a traffic shaping mechanism over traffic policing, where the motivation is to avoid dropping messages when users exceed their quota. Now, what happens here is that quotas can either be enforced on the producer side or the consumer side to make things a little bit more confusing. But fortunately, in this case, we're only concerned with the produce quotas, so we're going to talk about that. So what does this look like from the user's perspective? Well, from the user's perspective, when a user exceeds their quota, the request will get placed onto an internal queue, where Kafka then controls the rate of which those requests leave the queue. Therefore, Kafka essentially makes sure that the user is in compliance with their quota set in place. Now, this comes with the real cost of that there needs to be enough space on the broker to hold all of these queued requests. But the good thing here is that Kafka makes sure that it stores only what's necessary. However, it turns out that there was a bug. Out-of-memory error, Java heap space. As you can see here, you can guess what's happening. There was some gradual growth in heap that grew out of control and eventually exhausted all of the on-heap memory. So hang on here. Let's take a step back, look at the symptoms. Brokers were crashing, being restarted on a regular basis. The reason for this was most likely as a result of users exceeding their produce quotas because we were getting a heap problem and because Kafka uses some traffic shaping mechanism to enforce quotas. So first thing when dealing with heap-based out-of-memory errors, let's grab a heap dump. You'll see on the right side of the screen here that there's a large retained heap. Now, this is a pretty good place to start looking, but we can't just go and tune things willy-nilly, so we should get a better understanding by first taking a look at the produce request lifecycle, or what it means to write messages to Kafka. So, if we start at the entry point in Kafka APIs, when a broker receives a request, it'll take that request, extract the message from it, and write that message to the underlying log on disk. After that, it'll wait some time for a callback to be called, in which if a user is over their produce quota or quota period, then a delay will be computed, and then it will be put onto an internal queue to be processed and sent back at some later time in the future. Finally, after that, before it returns, it will remove all references to the produce request so that the GC can reclaim its memory. And this is nice because after this point, the message would have already been extracted from the request and written to disk. So if we held on to the request after this point, then we would be unnecessarily taking up memory on the broker. But it turns out that this wasn't entirely true. Kafka wasn't actually clearing out all of the underlying references to the produce request. So what did we do? We filed a JIRA. This JIRA turned out to actually block the release, in which we then followed up by submitting a patch upstream. This patch got reviewed, merged in, and landed in Kafka 10.2. So you should probably upgrade Kafka. So that was our first issue, heap-based out of memory. Our second issue we faced had a slightly different behavior, so let's take a look at some of the symptoms. First, we were seeing that brokers were seeing some cascading failures all throughout the cluster. And then we were also seeing that some brokers were being restarted, and then when they go to start back up, they weren't able to. However, in some cases, brokers were able to boot up, but then they would suddenly fail again out of nowhere. So let's dig in. First, you shouldn't expect services to be available 100% of the time in distributed systems. Things can fail. And this is especially true for us since we host our services on AWS, where boxes can go up and down at any time. But still, this was pretty odd that our brokers were failing regularly, and even more odd that when they tried to come back up, they just couldn't at all. So to get a deeper understanding of that, let's first take a look at Kafka's HA model. Then, what happens when a broker goes down, and then finally, what happens when a broker comes back up. So for Kafka's HA model, Kafka has a concept of leaders and followers, where writes and reads are designated to various leaders in the cluster. And then followers are other brokers that simply just continuously pull from their respective leaders. Now, recall that brokers have topics, and topics have one or more partitions. So in this example, we'll see that the user events topic has 3 partitions, P0, P1, and P2, where the broker on the left is lead for partition 0, and the broker up top is lead for partition 1, and so on. Now consider the line in the middle. It says replicated here, which means that the user events topic is replicated. So in other words, the partitions are individually replicated onto other brokers. So again, in this example, broker on the left is lead for partition 0, but then it's also followers for partition 1 and 2. Broker on the top is lead for partition 1, but then also followers for partitions 0 and 2. So in essence, Kafka tries to balance leadership among brokers so that it can basically say that a broker is lead for only a subset of all the partitions in the cluster. So to illustrate that further, say we ignore replication factor for a second, and we have 5 brokers, 1 topic, and 50 partitions. In this case, a broker will be lead for about 10 partitions on average, or 50 partitions divided by 5 brokers. And in other words, a broker will process both read and write requests for 10 out of 50 partitions for that given topic. Now, if we consider replication factor with it being set to 3 on the topic, we'll see that there will be 2 additional copies for each partition, ideally living on other brokers in the cluster. And I say ideally because it doesn't have to, but it should. So again, replication is pull-based, where brokers also may act as a follower, and they continuously pull messages from their leaders. Now, I would like to add that each leader maintains something called an in-sync replica set, or ISR. And these ISRs essentially just represent all followers that are currently caught up to the leader. Now, If a follower is being lagged for whatever reason, or it just completely got stuck, then the leader will then remove the follower from its ISR. And this is especially important for when brokers fail over, because on a failover, only followers that are in the ISR currently may be elected as a new leader. So that's Kafka's HA model. Now let's take a look at what happens exactly when a broker goes down. So first, in Kafka, there's something called a controller. There's one of them per cluster. And this controller manages states of partitions and replicas using state machines. And replicas is just another name for a follower. With that said, it's incredibly important for the controller so that the state machines allow it to administrate tasks such as determining which brokers are leader for which partitions on cases where things fail over, for instance. Now, the partition specifically internally has many different states and state transitions. Today, we're interested in the case where a partition transitions from the online state into the offline partition state. And this will happen for generally many partitions at once, because when a broker goes down, then since it's lead for many subsets of all partitions in a cluster, then all of those partitions will go down as well. So as for failing or going down, for the brokers, there are two cases: clean and unclean shutdown. On a clean shutdown, a broker will initiate a controlled shutdown sequence where it sends a request to the controller. The controller will see that, and then it will preemptively move partition leadership off of that shutting down broker and onto a different broker that's alive in the cluster. After that, it'll send a response back to the broker in which that shutting down broker will proceed on with its local shutdown tasks. On an unclean shutdown, it works a little bit differently, since the brokers won't necessarily be able to notify the controller that it's shutting down. So, for a little bit of context, when a broker boots up, it will first register itself in Zookeeper, and basically it just writes some metadata saying that it's alive, and it does this by writing an ephemeral Z node. So when a broker goes down, when it dies, so does the Zookeeper session. When the Zookeeper session dies, the ephemeral Z node goes away. Now, the controller in the cluster will have listeners that listen for these types of events, where it'll take all of the partitions that that downed broker was leader for, and then move them into the offline partition state. And it does this simply by just writing some metadata to a map locally. After that, it'll take those freshly offline partitions, and then it'll transition them back into the online partition state, but this time onto another live broker on the cluster. So that's what happens when a broker goes down. Now, what happens when it comes back up? Well, when a broker starts up, it has to initialize many things. And among these things, there's one important one, which is the log manager. And essentially what this thing does is it makes sure that the broker completely reads all of the partitions from disk and into memory when a broker starts up. After that, the broker will register itself in Zookeeper, telling the cluster that it's alive, as we just described. And then it'll begin fetching messages from their respective leaders under normal operation. OK, so that was that for shutting down, but what's the point of all this? Well, the major insight here is that that's a lot of work. That's a lot of work that brokers need to do when a failover occurs. And that's a lot of work for brokers to do when restarts happen. Essentially, work is a function of the number of partitions on a broker. More partitions means more work. And more work means more time required for brokers to recover when they boot up. So this could take a while. If you remember, we run thousands of partitions per broker. And unfortunately, at the time, our automation didn't consider this. So our automation, although it would restart brokers just fine all day, recovery would take longer than expected, where our automation would catch this, detect it, time out the broker, and proceed to restart it again. And this would happen repeatedly. Essentially, our automation was a little too aggressive. So what did we do? We introduced a recovery state into our automation's own state machine so that it would allow brokers enough time to recover without interfering. In addition to that, we added additional monitoring and alerting around the case where recovery takes unusually long, but in this case, we page a human rather than attempting automatic remediation. So that was our second issue we faced. The third and more recent issue had a similar behavior, but this time it was less straightforward. Let's take a look at the observed behaviors. First, we were seeing long periods of stability. Everything was behaving just fine, then one day, suddenly brokers started crashing. And to make matters worse, when brokers tried to boot up, they were crashing at various stages of the boot up process. So this wasn't a deterministic thing. And finally, we were seeing unreplicated partitions to make matters worse. And also, brokers were seeing request timeouts from various inter-broker communications. And this time it was for certain that our automation was not interfering. So recall that when brokers boot up, they need to load all of their partitions. Now, if you think about it, what does it exactly mean to load a partition? How does this exactly work internally? So let's dig in. The anatomy of a partition, which is also sometimes called a log, consists of a sequence of many log segments. And these log segments are created under some frequency that's determined by when a log should be rolled, which is determined by either time or size. So if you look in the example here, if a log is rolled every 3 hours, then you'll end up with 8 log segments per day. So in aggregate, that amounts to many files on disk. There are many log segments there. And remember, we have thousands of partitions per broker. That's a lot of file descriptors. We were seeing tons and tons being created as logs are being rolled. So, again, logs completely load all of their partitions and log segments. Now, I would like to add that Kafka does try to do a good job in making sure that brokers only use file descriptors for only the active log segments. And where this deviates is when logs are currently being rolled, as you may know, because the broker will temporarily hold on to file descriptors for old log segments until the roll is complete. So if we look back at the service's operational logs, the logs that you're normally used to, the tail F, you will see the following. IO exception, too many files in the system. What does this mean? Well, we need more file descriptors. We were completely maxing out on our limit. And what did we do to fix this? We increased the limit on the process and the system as well. This is in the syscontrol and the limits.conf, where the idea is to basically reserve enough for the process and have or maintain a sufficiently large enough buffer for the rest of the system. So as a general rule of thumb, we recommend about 1.5 file descriptors per log segment. And now technically, log segments consist of 3 actual files on disk, the data, index, and time index files. However, through our extensive testing, we did find that it was about 1.5 per log segment. And this is for many reasons, and one of which is that Kafka, again, tries to hold on to file descriptors only for the active log segments. But the more important thing to consider are the number of inputs that are involved when thinking about this problem. First, you need to consider the number of topics and their partitions and the replication factor. Then you take that, divide it by the number of brokers. Then you have to consider your log segments, basically how many logs you have and how often they're rolled, calculate that against the retention time. And then you come up with those two resultants, you multiply them together, multiply them again by a buffer, in this case 1.5, and then you get your configuration. So we did exactly that. But our brokers were still not able to boot, not yet anyway. So if we dig deeper and look at some of the observed behaviors, we'll see that our brokers were failing in a cascading way. They were being restarted, not able to boot up. Automation wasn't interfering. Some brokers did boot, but then suddenly died again. Not sure what's going on here, so let's take a look back at the logs, and we'll see 3 different errors. First, on a replica fetcher thread, on a fetch, Kafka storage exception while appending to a log. In a request handler, when broadcasting metadata, IO exception map failed. And lastly, in a Kafka server starter thread, fatal error during startup. Prepare to shut down. Another IO exception map failed. It was all over the place. So, could this be another out-of-memory problem? Or could this be another memory leak? Well, the funny thing is that memory wasn't even being saturated on these brokers at the time of the crashes. GC logs were behaving just fine, or the GC was behaving just fine. We were getting acceptable evacuation pause times. Heat pressure was totally fine. Cross-checking that with the system memory, using HTOP, we see the same behavior, about 5 gigs out of 16 utilized. But now if you take a closer look at the log, you'll see that it references something called the file channel implementation, the map method. Now if we dig into that map method in the C code, we'll see that it references native memory. Specifically, it tries to allocate memory-mapped byte buffers. Now this makes sense because Kafka internally heavily leverages native memory. But basically, this was not a heap problem. The problem, though, was a small one where Kafka uses native memory for many different things, and these kinds of things aren't readily apparent in the GC logs or heap dumps. Though, fortunately, there are many other ways to diagnose these types of problems. We chose to investigate by correlating various JMX metrics using various JMX tooling. So if we look back at the log, we'll see that it references the request handler in one of them. So we thought, could this be an issue around the network? Something around the network parts of the code? Well, to dig in, we look at Kafka's network processor threads. In our case, we have 3 of them. And we're looking for the idle percentage of these threads where, if you look at the top, basically it was 100% idle everywhere. Okay, so we weren't sure if this was legit, so we wanted to correlate this with some other metrics. So next we looked at the request queue size mbean. As you can see at the top again, it says 0. Basically, no requests were in flight. But we were sending requests, so that was pretty odd. So still not sure, a little bit more confident, but still needed to dig. So we dig some more, and after some more digging, after some time, we found out that we were quite confident that the problem wasn't a result of some issue with the network part of the code. Great, so now what? Well, remember, we are dealing with a native memory problem here and not a heap problem, so where do we look next? We look at NIO. And specifically, we look at the buffer pool mapped mbean. We check out the count, and what did we find? We found out that our mapped byte buffers were growing uncontrollably. Okay, this was our smoking gun. So piling on top of this, we cross-check that with the system. All you do is check out proc with PID on maps, take them all up and count them up. What do we get? That's a lot of memory maps. So with that in mind, firstly, why would this cause brokers to fail? We had plenty of memory, disk, and other resources on the brokers to handle these cases. But actually, that was a lie. So if you take a look here, we check out proc sys, VM, max map count, we get a result of 65,535 maximum memory counts. Okay, that sounds like a lot or a little, not sure. What's the context here? I mean, it seems fine, but wait, remember that we're running many partitions on a broker, where these partitions have many log segments, and these log segments must be loaded and read completely when a broker boots up. So think about it again. Is that a lot of memory maps? Well, if you're doing some thinking about the JVM case, you'll see that, just to cover it, we were running 64-bit JVM, so there's no funny business going on here. Okay, so pause, think about it again. Is that a lot of memory maps? Well, yes, it was. It turns out that we didn't have enough memory mapped regions available to us. But why does this matter? Because our brokers were surviving restarts in the past for the longest time, and this was just another day in the operational side of things. But there was also another thing in that we weren't able to reproduce this in our staging environments. However, there was a subtle difference. Log rolling. So we needed there to be enough traffic or retention to force enough logs to be rolled so that it would in turn create more log segments, which then would result in more memory mapped files being required on a boot up. So this is why memory looked fine during a sudden crash. And this is why brokers would crash when they go to recover their logs. So what did we do? We fixed it. We fixed this by increasing the limit on the VM max map count. And the idea is similar to before, where you want to preserve enough for the process while maintaining a sufficiently large enough buffer for the system. So great. Our brokers were able to boot successfully once again. Although that was definitely a lot of file descriptors and memory maps that we saw, so for completeness, we ran with this configuration and staging for a little while longer under heavy load so that enough logs would be rolled on a frequent basis. We had retention set quite high so that we could rule out the potential for another leak scenario, but this time, instead of the heap, we wanted to rule it out in the case for file descriptors or memory maps. After all of that, everything turned out to be fine. So to wrap up, today we covered Kafka and its internals. It's pretty nice and flexible in that it can satisfy many different things in production. But with this flexibility comes a real operational complexity trade-off, where there are many things to configure and understand deep down at scale. And fortunately, at Heroku, we offer Apache Kafka as a fully managed service, so you don't have to worry about that. We take care of a lot of the operational burdens for you so that you can focus on writing your data-intensive applications. Today, we covered 3 different points of our journey in our time operating Kafka in production. We covered how quotas work and how we discovered a release blocking heap-based out-of-memory bug around quota management and how we shipped a patch that landed in 10.2. We covered how Kafka achieves HA and a specific case where our automation was aggressively remediating brokers on recovery. And finally, we also covered how partitions are implemented in Kafka internally and what kinds of resources they need. Again, I'm Jeff Chow. You can reach me at jchow@heroku.com. If you want to chat, I'm happy to. I'm happy to chat about all things Kafka, distributed systems, and streaming data infrastructure. I'll be around during the rest of the conference and during office hours. Thank you.
Thank you. So if anyone has a question, we have a few minutes. You get a quota, no more than 3 questions per conference.
Okay. For your second case, I didn't follow. Why was your automation constantly restarting brokers?
So the question was, why was our automation restarting brokers in the second case? Well, that's because the brokers in our configuration have many thousands of partitions on them. And there are many different things to do when a broker comes up and goes down, or goes down and comes up. And basically, it might take a while per broker for it to recover. So our automation would time it out as it goes to recover. And then it would just restart it in the middle of recovery.
So it's essentially to detect a possibly failed recovery and resolve it by kicking off another restart, which would require recovery? So the question was, the follow-up was that, is it like a timed thing, right? Was that correct? I mean, it was restarting something that was trying to recover. That was the goal of the automation?
That's correct. So the broker would try to recover just fine, but then the automation would be a little too aggressive, and it would shut it down and let it try again because it would say that it's taking too long. But it was legitimately taking too long because there's lots of things to do for when a broker starts up, if there are many partitions on the broker.
Okay. So I guess I've heard that people who run Kafka sort of restart because when they get into a weird state, their way out of that state is to restart it, sort of like the Windows laptop problem.
Right. So you definitely don't want to restart anything in a distributed systems like a Windows laptop. You want to do it in a controlled manner in general, because you might have various problems that are associated with that. Thundering herd, different cache issues, you don't know. Depends on the system. But in this particular case, you want to treat the different states of when a broker restarts independently. So it's down, it's starting up, it's stabilizing, and it's recovering. So the case where it's recovering, you might not know how long it takes to recover, depending on what your configuration is. The point is, you have to balance between the time to detect a problem and the time to take action. If you want to detect it and act quickly, potentially you could get very quick restarts on your system and get back to availability again. But that might not work in every case, because some cases you might want to take some more time to restart.
All right, thank you.
Very quick.
Hi. Why did you decide to change the configs in the box itself rather than maybe like putting fewer partitions on a machine or like increasing the segment size?
Mm-hmm. So that's a good question. The question is, why didn't you just limit the number of partitions? Now that certainly would be an option, but and that's certainly a thing you can do since Kafka scales pretty well horizontally. If you are running into partition problems, just add more boxes. However, that might not be the most cost-effective way of dealing with things. You want to kind of inch out every single amount of performance that you can on a box, and then after that, if you're seeing diminishing returns or signs of it, or some other trade-off that you aren't willing to make, then you can scale it out. So we thought that it would be a worthwhile effort to see what an individual broker could do. And also, in addition to that, no one has really dealt with that type of thing before. And with that, we were able to surface a handful of bugs that we've patched for upstream as well. Some of them are in 10.2. Some of them, I think, are 10.2.1, which was released today. And I think some would be scheduled for 0.11, but still up in the air for that.